Hello everyone. Welcome back to my course Aerospace Engineering, Rocket Science Basics. In this video, we will talk about fundamentals of rocket engine thrust and performance. Also, I will be thankful if you give me feedback about this course to make it better and more useful for you. Please write down your thoughts in the comment section or reach out to me via the email provided in my profile. Rocket principles. At its most fundamental level, a rocket is simply a chamber that contains a gas under pressure. This chamber has a small opening at one end, which allows the gas to escape. As the gas exits, it creates a force in the opposite direction, known as thrust, which propels the rocket forward. This principle, while simple, forms the foundation of all rocket propulsion. A familiar and easy to understand example of this concept is a balloon. When a balloon is filled with air, the rubber walls of the balloon compress the air inside. The air pushes outward, balanced by the inward tension of the balloon's elastic walls. When the nozzle of the balloon is released, the compressed air rushes out through the opening. In response, the balloon shoots off in the opposite direction. Although rockets are often associated with massive vehicles that carry satellites into orbit or send spacecraft to the moon and other planets, the basic principles are the same as those demonstrated by a balloon. The key difference lies in how the pressurized gas is generated. While a balloon relies on compressed air, space rockets produce gas through the combustion of propellants. These propellants can exist in solid, liquid, or hybrid forms, and their chemical reactions generate the high-speed gases necessary to produce thrust. An interesting aspect of rocket history is that humans have been using rockets and rocket-powered devices for over 2,000 years. Ancient civilizations experimented with simple gunpowder rockets for fireworks and military purposes. However, it is only in the last 300 years that scientists and engineers have been able to approach rocket design with a true understanding of the underlying physics and mechanics. This scientific foundation has allowed modern rockets to reach unprecedented speeds and distances, enabling space exploration and satellite deployment. The modern science of rocketry owes much to the groundbreaking work of the great English scientist Sir Isaac Newton. In 1687, Newton published a book titled Philosophiae Naturalis Principia Mathematica, which laid out the fundamental physical principles governing the natural world. Today, this work is commonly referred to simply as the Principia. Within its pages, Newton described three essential laws that explain how all objects move, whether they are on Earth or traveling through space. These principles, now universally known as Newton's laws of motion, form the foundation for understanding and designing rockets. Thanks to these laws, engineers have been able to construct some of the most remarkable rockets of the 20th century, including the Saturn V, which carried astronauts to the moon, and the Space Shuttle, which enabled repeated missions into low Earth orbit. Newton's laws of motion can be stated in simple form. The first law states that an object at rest will remain at rest, and an object in motion will continue moving in a straight line at a constant speed, unless it is acted upon by an unbalanced force. This law explains why a rocket cannot start moving on its own. It must have a force applied to overcome its inertia. The second law states that force is equal to mass multiplied by acceleration. This relationship allows engineers to calculate how much force a rocket engine must produce to accelerate a rocket of a given mass. In other words, it links the weight of the rocket to the power of the engines needed to launch it. The third law states that for every action, there is an equal and opposite reaction. This is the law that directly explains rocket propulsion. When a rocket expels gas out of its engine at high speed, the rocket is pushed in the opposite direction. It is the same principle demonstrated by the balloon example, but on a much larger scale with far more powerful forces at work. While these laws may seem simple, they are extraordinarily powerful tools. By applying Newton's laws of motion, scientists and engineers can make precise calculations about rocket trajectories, speeds, and fuel requirements. Essentially, these three statements describe how all objects move, but when applied to rocketry, they unlock the ability to send spacecraft from Earth to orbit and beyond. Newton's first law of motion. Newton's first law of motion may seem like an obvious statement of fact, but understanding it fully requires a clear grasp of three key terms: rest, motion, and unbalanced force. Rest and motion can be thought of as opposites. An object at rest is one that is not changing its position relative to its surroundings. For example, if you are sitting still in a chair, you are considered to be at rest. However, this term is relative. Your chair might actually be one of many seats on a speeding airplane. What matters is that you are not moving relative to your immediate surroundings. If rest were defined as a total absence of motion, it would not exist in nature at all. Even when sitting at home, you are still moving because the Earth is spinning on its axis, orbiting the Sun, which is moving through a rotating galaxy, and that galaxy is traveling through the universe. In other words, while you may feel still, you are actually moving at incredible speeds, possibly hundreds of kilometers per second. Motion, like rest, is a relative term. All matter in the universe is constantly moving, but in the context of Newton's first law, motion refers specifically to a change in position relative to surroundings. A ball resting on the ground is at rest, but once it begins to roll, it is in motion because its position is changing relative to the ground. Similarly, when you are seated in an airplane, you are at rest relative to the interior of the cabin, but if you stand up and walk down the aisle, you are in motion. In the case of a rocket, motion begins when the vehicle leaves its launch pad, transitioning from a state of rest to a state of motion. The third term critical to understanding this law is unbalanced force. Forces are constantly acting on objects, even when they appear to be at rest. If you hold a ball in your hand, the ball is at rest because the forces acting on it are balanced. Gravity pulls the ball downward, while your hand exerts an upward force to hold it in place. These equal forces cancel each other out. If you release the ball, or if your hand moves upward, the forces become unbalanced. The ball then accelerates, changing from a state of rest to a state of motion. In rocket flight, the interplay of balanced and unbalanced forces is constantly at work. When a rocket sits on the launch pad, the forces are balanced. Gravity pulls the rocket downward while the solid surface of the pad pushes upward. The rocket remains at rest. As the engines ignite and generate thrust, the upward force becomes greater than the downward pull of gravity, creating an unbalanced force. This unbalanced force propels the rocket upward into motion. Later in its flight, as the fuel is consumed and thrust decreases, the forces gradually balance again. The rocket slows, reaches its highest point, and eventually falls back to Earth under the influence of gravity. Objects in space also respond to forces in the same way as objects on Earth. A spacecraft traveling through the solar system is constantly in motion. If all the forces acting on the spacecraft are balanced, it will continue moving in a straight line indefinitely. This ideal situation occurs only when the spacecraft is far away from any large sources of gravity, such as planets, moons, or stars. When a spacecraft approaches a massive body, like Earth or another planet, the gravitational pull from that body creates an unbalanced force. This unbalanced force alters the spacecraft's straight-line path, curving its trajectory. A familiar example of this occurs when a satellite is launched into orbit. If the rocket propels the satellite fast enough along a path parallel to Earth's surface, the satellite enters a curved orbit. In this orbit, the pull of Earth's gravity constantly redirects the satellite, keeping it moving around the planet rather than falling straight down. As long as no other unbalanced forces act on the satellite, such as friction from the thin gas molecules present in low Earth orbit or deliberate thrust in the opposite direction, the satellite will continue orbiting indefinitely. Now that the three major terms of the first law, rest, motion, and unbalanced force, have been explained, Newton's first law can be restated in the context of rockets and space travel. If an object, such as a rocket, is at rest, it requires an unbalanced force to initiate motion. Once the object is already moving, an unbalanced force is necessary to stop it, to change its direction from a straight line path, or to alter its speed. This principle explains why rockets must generate thrust to lift off from the launch pad, why spacecraft need carefully planned maneuvers to change course in space, and why satellites continue to orbit once they are in motion. Newton's third law of motion. For now, we will move past the second law and focus on Newton's third law. This law states that for every action, there is an equal and opposite reaction. In simpler terms, whenever one object exerts a force on another, the second object exerts a force of equal magnitude in the opposite direction. A simple, everyday example makes this principle easy to visualize. Imagine stepping off a small boat that is not securely tied to a dock. As you push yourself forward to step onto the pier, the boat pushes back in the opposite direction. The harder you push, the more the boat moves backward. This is a direct demonstration of action and reaction forces at work. In the context of rocketry, Newton's third law is the fundamental principle that explains propulsion. When a rocket engine expels gas downward at high speed, the rocket experiences an equal force pushing it upward. The action is the gas being forced out of the rocket engine, and the reaction is the rocket moving in the opposite direction. Without this principle, rockets would not be able to lift off from the launch pad, travel through the atmosphere, or navigate in space. A rocket can lift off from a launch pad only because it expels gas out of its engines. The rocket pushes on the gas, and the gas, in turn, pushes back on the rocket. This push and pull relationship is a direct demonstration of Newton's third law of motion, which states that every action has an equal and opposite reaction. A simple analogy can help make this idea more tangible. Imagine a rider standing on a skateboard that is at rest. When the rider jumps off the skateboard, the jump is the action. The skateboard moves in the opposite direction as a result, which is the reaction. At first glance, it may seem that the skateboard moves farther than the rider, suggesting it experienced a greater force. However, this is not the case. The apparent difference in motion occurs because the skateboard has much less mass than the rider. The same force produces a larger acceleration in the skateboard due to its smaller mass, a concept that will be explained in detail when discussing Newton's second law. In a rocket, the action is the expulsion of exhaust gases out of the engine, and the reaction is the rocket being propelled in the opposite direction. For a rocket to lift off from the launch pad, the thrust produced by the engines must be greater than the weight of the rocket. Once in space, however, even small amounts of thrust can change the rocket's direction or speed, because there is no air resistance to oppose the motion. One common question about rockets is how they can function in the vacuum of space, where there is no air for them to push against. The answer lies entirely in Newton's third law. Returning to the skateboard analogy, when the rider jumps on Earth, the surrounding air actually slows down both the rider and the skateboard due to friction, which scientists call drag. In space, there is no air to impede the motion of the rocket or its exhaust gases. This means that rockets are actually more efficient in space than in the atmosphere. Exhaust gases can escape freely without resistance, allowing the rocket to convert more of its engine energy into forward motion. Newton's second law of motion. Newton's second law of motion is essentially a mathematical description of how forces affect the motion of objects. The law relates three key quantities: mass, acceleration, and force. Using simple symbols, the law can be expressed as force equals mass multiplied by acceleration. Here, F represents force, M represents mass, and A represents acceleration. This equation can also be rearranged to solve for acceleration or mass. Acceleration equals force divided by mass. Mass equals force divided by acceleration. The first version is the one most commonly cited when discussing Newton's second law. To understand this concept more concretely, let's consider the example of an old-fashioned cannon. When the cannon is fired, an explosion propels the cannonball out of the barrel at high speed. At the same time, the cannon itself recoils backward. This backward movement of the cannon demonstrates Newton's third law. The action of the cannonball being pushed forward produces an equal and opposite reaction on the cannon. The force acting on both the cannon and the cannonball is the same. However, the effect of this force on each object is determined by Newton's second law. For the cannon, the force equation can be written as force equals mass of the cannon multiplied by acceleration of the cannon. For the cannonball, the equation is force equals mass of the cannonball multiplied by acceleration of the cannonball. Because the same force acts on both the cannon and the cannonball, we can combine the two equations. Mass of the cannon multiplied by acceleration of the cannon equals mass of the cannonball multiplied by acceleration of the cannonball. This equation shows that the acceleration of an object is inversely proportional to its mass when the same force is applied. In other words, the cannon, having a large mass, experiences only a small acceleration. The cannonball, having a much smaller mass, experiences a much larger acceleration, allowing it to fly rapidly toward its target. Newton's second law is therefore a powerful tool for understanding and predicting motion. In rocketry, it explains how a rocket's mass and engine force determine its acceleration during launch, ascent, and maneuvers in space. By calculating the mass of the rocket and the thrust produced by its engines, engineers can precisely predict how quickly the rocket will accelerate and how it will behave at different stages of flight. We can apply the principles discussed with the cannon and cannonball directly to rockets. In this case, the mass of the cannonball is replaced by the mass of the gases being ejected out of the rocket engine, and the mass of the cannon is replaced by the mass of the rocket itself, moving in the opposite direction. The force in this scenario is the pressure created by the controlled explosion occurring inside the rocket engines. This pressure accelerates the gas one way and the rocket in the other, demonstrating Newton's second, third laws in action. Unlike the cannon, which experiences thrust for only an instant, a rocket's engines produce continuous thrust as long as they are firing. Another key difference is that the mass of a rocket changes during flight. The rocket's total mass is made up of all its components: engines, propellant tanks, payload, control systems, and most importantly, the propellant. The propellant usually accounts for the largest fraction of the rocket's mass, but this mass steadily decreases as the engines burn fuel. Because Newton's second law states that force equals mass multiplied by acceleration, the rocket's decreasing mass affects its acceleration. As the mass of the rocket decreases, the same force produces greater acceleration. This is why rockets start off moving relatively slowly and then accelerate faster and faster as they climb into space. Newton's second law is especially useful when designing efficient rockets. To place a rocket into low Earth orbit, it must reach speeds exceeding 28,000 kilometers per hour. To escape Earth entirely and enter deep space, a rocket must reach speeds above 40,250 kilometers per hour, known as escape velocity. Achieving these speeds requires maximizing the action force generated by the engine in the shortest possible time. In practical terms, the engine must burn a large mass of fuel quickly and expel the resulting gases at high speed. In simpler terms, Newton's second law for rockets can be restated as: the greater the mass of rocket fuel burned and the faster the exhaust gases can escape the engine, the greater the thrust of the rocket. Putting Newton's laws together. All three of Newton's laws work together to explain how rockets move. Newton's first law, law of inertia. An unbalanced force must be exerted for a rocket to lift off from a launch pad, or for a spacecraft in space to change its speed or direction. Newton's second law, force mass, acceleration. The amount of thrust produced by a rocket engine depends on the mass of the fuel burned and how fast the gas escapes the engine, expressed as force equals mass multiplied by acceleration. Newton's third law, action and reaction. The motion of the rocket is equal in magnitude and opposite in direction to the action of the exhaust gases expelled from the engine. Together, these three laws explain the fundamental principles of rocket propulsion and allow engineers to calculate and design rockets capable of reaching orbit, traveling to other planets, or leaving Earth entirely. Rocket engines and their propellants. Most modern rockets operate using either solid or liquid propellants. It is important to understand that the term propellant does not refer solely to fuel, as it might seem. Instead, it encompasses both the fuel and the oxidizer. The fuel is the substance that undergoes combustion to release energy, but for this combustion to occur, an oxidizer, usually a form of oxygen, must also be present. This requirement distinguishes rockets from jet engines. Jet engines, such as those on airplanes, rely on oxygen from the surrounding air to burn their fuel. Rockets, however, cannot rely on external oxygen because they must operate in space where no air exists. Therefore, rockets must carry both their fuel and their oxidizer with them. The combination of these two components, the propellant, is what allows the rocket to produce thrust, both in Earth's atmosphere and in the vacuum of space. Solid rocket propellants are dry to the touch and contain both the fuel and oxidizer chemically combined within a single substance. Typically, the fuel is made from hydrogen compounds and carbon, while the oxidizer is composed of oxygen compounds. When the rocket engine ignites, the propellant burns, producing hot gases that generate thrust. Liquid propellants, on the other hand, are usually gases that have been cooled until they liquefy. In liquid propellant rockets, the fuel and oxidizer are stored in separate containers. When the engine fires, the fuel and oxidizer are carefully mixed inside the combustion chamber, where they react to produce high-speed gases and thrust. Solid propellant rocket engines. Solid propellant rockets feature the simplest type of engine. The main components include a nozzle, a case, insulation, propellant, and an igniter. The case is typically a relatively thin metal shell lined with insulation to prevent the propellant from burning through. Inside the insulated case, the propellant is packed tightly. Many solid rockets include a hollow core running through the propellant. Rockets without a hollow core must be ignited at one end, with the propellant burning gradually toward the other end. In all cases, only the surface of the propellant burns. However, the hollow core design increases the surface area available for combustion. This causes the propellant to burn from the inside out at a higher rate, producing gases that escape at greater speeds and generate significantly more thrust. Some propellant cores are even star-shaped to maximize the burning surface area further. Solid propellants can be ignited in several ways. Early rockets, like fire arrows, used fuses, but these were unreliable and sometimes dangerous. Modern rockets often use electric igniters. In this method, an electric current travels through wires to a small wire inside the rocket, which heats the propellant to its combustion point. Advanced igniters may include a small chemical charge that ignites first and then lights the main propellant. For very large rockets, igniters can even be miniature rocket engines themselves. These small engines blast flames and hot gas into the hollow core of the main rocket, igniting the propellant across the entire surface almost instantaneously. The nozzle of a solid propellant rocket is the opening at the back of the rocket through which hot gases escape. The narrowest part of the nozzle is called the throat, and just beyond it is the exit cone. The nozzle's primary purpose is to accelerate the exhaust gases as they leave the rocket, maximizing thrust. A simple analogy is a garden hose with a spray nozzle. With the nozzle fully open, water flows slowly and produces less force. As you reduce the diameter of the opening, the water speeds up and pushes with greater force. Rocket nozzles work on the same principle, except they are designed to handle extremely hot and high-pressure gases. Like the rocket case, the nozzle must also be protected from heat. Insulation lines the nozzle and gradually erodes as the hot gases pass through. Tiny pieces of insulation become extremely hot and break away, carrying heat with them and helping to protect the nozzle from damage. Liquid propellant rocket engines. The other main type of rocket engine uses liquid propellants, and these engines are considerably more complex than solid propellant rockets. In fact, solid rockets were in use for over 700 years before the first successful liquid propellant rocket engine was tested. A liquid propellant engine requires separate storage tanks, one for the fuel and one for the oxidizer, as well as pumps, a combustion chamber, and a nozzle. The fuel in a liquid propellant rocket is usually kerosene or liquid hydrogen, while the oxidizer is commonly liquid oxygen. The fuel and oxidizer are combined in the combustion chamber where they burn, producing extremely high temperatures and pressures. The expanding gases then escape through the nozzle at the rear of the rocket. To maximize efficiency and thrust, the propellants must mix as thoroughly as possible. Small injectors located at the top of the chamber spray the fuel and oxidizer simultaneously, ensuring complete mixing and rapid combustion. Because the combustion chamber operates under very high pressure, the propellants must be actively forced into it. Powerful, lightweight turbine pumps are used to transfer the fuel and oxidizer from their storage tanks into the chamber. These pumps are an essential part of the liquid engine system and add significant complexity and weight compared to solid rockets. Weight is always a critical factor in rocket design. In general, heavier rockets require more thrust to lift off from the launch pad. Liquid propellant engines are heavier than solid engines because of the additional components such as tanks, pumps, and fuel lines. To reduce weight, engineers often construct the exit cone of the nozzle from very lightweight metals. However, the extreme heat and high-speed gases passing through the nozzle would quickly melt thin metal walls, so a cooling system is necessary. One highly effective cooling method takes advantage of the extremely low temperature of liquid hydrogen. Hydrogen becomes a liquid at -253 degrees Celsius. Before entering the combustion chamber, the liquid hydrogen is circulated through small tubes that line the walls of the nozzle's exit cone. In cross-section, these walls resemble the edge of corrugated cardboard. The hydrogen absorbs the heat entering the walls, preventing them from melting. And at the same time, the hydrogen gains thermal energy, which makes it more energetic when injected into the chamber. This process is called regenerative cooling, and it is one of the most efficient cooling systems used in modern liquid propellant rockets. Engine thrust control. Controlling the thrust of a rocket engine is critical for successfully placing payloads, such as satellites, into orbit. If the thrust is too high or applied at the wrong moment, a satellite may end up in the wrong orbit or travel too far into space to be useful. Conversely, too little thrust can prevent the payload from reaching orbit at all, causing it to fall back to Earth. Liquid propellant engines allow precise thrust control by adjusting the amount of fuel and oxidizer entering the combustion chamber. A computer in the rocket's guidance system calculates the exact thrust required at any given moment and regulates the flow rate of the propellants. For complex missions, such as trips to the moon, the engines may need to be started and stopped multiple times. In liquid engines, this is achieved simply by turning the propellant flow on or off, making them highly adaptable during flight. Solid propellant rockets, however, are more difficult to control. Once ignition occurs, the propellant burns continuously until it is exhausted. Slowing down or stopping the burn mid-flight is challenging. In some designs, fire extinguishing systems or remote-controlled hatches can release chamber pressure to halt thrust, but these methods are complicated and not always reliable. Engineers also manage the burn rate of solid propellants by carefully designing the shape of the hollow core that runs through the propellant. Many cores are star-shaped. Initially, the large surface area allows a rapid burn and high thrust. As the star points burn away, the surface area decreases, reducing the rate of combustion and temporarily lowering thrust. The Space Shuttle used this technique to minimize vibrations during the early stages of its ascent into orbit. Important safety note. Even though most rockets used by governments and research organizations are highly reliable, building and firing rocket engines is extremely dangerous. Individuals should never attempt to construct their own engines. Even seemingly simple rocket engines involve complex engineering considerations, including case wall strength, propellant packing density, nozzle design, and propellant chemistry. Many home-built engines have exploded, causing serious injury or death. Rocketry should always be approached with professional guidance and appropriate safety precautions. Liquid rocket engine thrust. On this slide, we examine a schematic diagram of a liquid rocket engine. Liquid rocket engines have played a major role in spaceflight and aerospace research. They were used on the Space Shuttle to place humans into orbit, on many unmanned launch vehicles to deploy satellites, and on several high-speed experimental aircraft developed after World War II. In a liquid rocket engine, both the fuel and the oxidizer are stored on board in separate tanks. These propellants are pumped into a combustion chamber where they are mixed and burned. The combustion process produces extremely hot exhaust gases at very high pressure. These gases are then directed through a nozzle, which accelerates the flow to very high speeds. Thrust is generated as a direct result of Newton's third law of motion. The action of the exhaust gases leaving the engine produces an equal and opposite reaction that pushes the rocket forward. The amount of thrust produced by a rocket engine depends on several key factors. These include the mass flow rate of the exhaust gases moving through the engine, the velocity at which the exhaust leaves the nozzle, and the pressure at the nozzle exit. All of these quantities are strongly influenced by the design of the rocket nozzle. The smallest cross-sectional area of the nozzle is known as the throat. At the throat, the exhaust flow becomes choked, meaning the Mach number reaches a value of 1.0. Under these conditions, the mass flow rate, written as m dot, is fixed by the throat area. Beyond the throat, the nozzle expands outward. The ratio of the exit area AE to the throat area determines both the exhaust exit velocity VE and the exit pressure PE. The pressure at the nozzle exit is equal to the surrounding free stream pressure only at a specific design condition. Because this is not always the case, a more complete thrust equation must be used. If the surrounding free stream pressure is represented by P0, the thrust produced by the rocket engine can be written as thrust equals mass flow rate multiplied by exhaust velocity plus the difference between the exit pressure and the surrounding pressure multiplied by the exit area. This equation shows that the thrust comes from two sources. The first term represents the momentum carried away by the exhaust gases. The second term represents the pressure difference between the nozzle exit and the surrounding environment. It is important to notice that there is no term involving free stream mass times free stream velocity in this equation. This is because rockets do not take in any external air. All of the working fluid and oxidizer are carried on board. As a result, rockets are capable of producing thrust in a vacuum where there is no surrounding air and no external oxygen source. Because rockets carry their own oxidizer, they can operate in space where no atmosphere exists. This is fundamentally different from gas turbine engines and propellers. Turbine engines and propellers rely on the surrounding air both as a working fluid for propulsion and as a source of oxygen for combustion. Without an atmosphere, these systems cannot function, whereas rockets remain fully operational. The thrust equation described above applies to both liquid propellant and solid propellant rocket engines. In addition, rocket performance is often described using an efficiency parameter known as specific impulse, which simplifies the analysis of rocket engines and allows meaningful comparisons between different designs. The actual process of mixing and burning fuel and oxidizer inside a rocket engine is extremely complex. The propellants must burn efficiently and stably without extinguishing the flame or causing destructive pressure oscillations. Designing a system that can achieve this reliably under extreme temperature and pressure conditions requires advanced engineering and deep scientific understanding. In this case, the phrase is absolutely true. It really does take a rocket scientist to make it work. Solid rocket engine thrust. On this slide, we show a schematic diagram of a solid rocket engine. Solid rocket engines are widely used in air and air-to-ground missiles, in model rockets, and as booster stages for satellite launch vehicles. Their popularity comes from their mechanical simplicity and reliability. In a solid rocket, the fuel and oxidizer are mixed together into a single solid propellant and cast into a solid cylindrical shape. A hole running through the center of the cylinder acts as the combustion chamber. When the propellant is ignited, combustion occurs only on the exposed surface of the propellant. A flame front forms and gradually burns into the solid mixture. This combustion process produces very large quantities of exhaust gas at extremely high temperature and pressure. The amount of exhaust gas produced depends on the surface area of the flame front. Engine designers carefully shape the hole through the propellant to control how the burning surface changes over time. Different hole geometries allow designers to control how thrust increases or decreases during flight. The hot exhaust gases are directed through a nozzle, which accelerates the flow and produces thrust according to Newton's third law of motion. The thrust produced by a solid rocket engine depends strongly on the design of its nozzle. The smallest cross-sectional area of the nozzle is called the throat. At the throat, the exhaust flow becomes choked, meaning the Mach number reaches a value of 1.0. Under these conditions, the mass flow rate, written as m dot, is determined by the throat area. Beyond the throat, the nozzle expands toward the exit. The ratio of the exit area AE to the throat area controls both the exhaust exit velocity VE and the exit pressure P. These parameters are critical in determining how efficiently the rocket converts thermal energy into thrust. The exit pressure of the exhaust equals the surrounding free stream pressure only under a specific design condition. Because this condition is not always met, a more general thrust equation must be used. If the free stream pressure is represented by P0, the thrust produced by the rocket is given by thrust equals mass flow rate multiplied by exhaust velocity, plus the difference between the exit pressure and the surrounding pressure multiplied by the exit area. Both for liquid and solid rockets, the thrust equation is the same. Only difference is the type of propellant used to generate the thrust. This equation shows that thrust comes from two sources. The first term represents the momentum of the exhaust gases leaving the engine, The second term accounts for the pressure difference between the nozzle exit and the surrounding environment. There is no free stream mass times free stream velocity term in this equation, because also solid rockets do not take in any external air. The oxidizer is mixed directly into the propellant, allowing solid rockets to produce thrust in a vacuum where no external oxygen is available. This explains why rockets can operate in space, while gas turbine engines and propellers cannot. Turbine engines and propellers depend on the atmosphere both as a source of oxygen for combustion and as the working fluid used to generate thrust. The thrust equation described here applies to both solid propellant and liquid propellant rocket engines. Rocket performance is often evaluated using an efficiency parameter known as specific impulse. This parameter applies to all rocket engines and greatly simplifies the analysis and comparison of different propulsion systems. We will come back to this parameter later. Rocket thrust summary. This diagram is a complete summary of how a rocket produces thrust, starting from the conditions inside the combustion chamber and ending with the thrust force that pushes the rocket forward. Everything on this page is connected, and the equations appear in a very deliberate order that mirrors the physical process inside a rocket engine. We begin with the physical picture on the right side of the image. The drawing shows a rocket engine with a converging-diverging nozzle. Inside the combustion chamber, fuel and oxidizer burn and create a very hot, high-pressure gas. The properties of this gas at rest inside the chamber are described using what we call total or stagnation conditions. These are labeled as total pressure P sub T and total temperature T sub T. Total means the values the gas would have if it were slowed down to zero velocity without losing energy. As the gas flows toward the nozzle, it first passes through the throat, which is the narrowest part of the nozzle. The throat area is labeled a star. A very important physical fact happens here. Once the chamber pressure is high enough, the flow becomes choked at the throat. Choked flow means the Mach number at the throat is exactly 1, so the gas is moving at the speed of sound. From that point on, no matter how much you increase downstream expansion, the mass flow rate through the engine is fixed by the chamber conditions and the throat area. The first equation presented is the mass flow rate equation. This equation tells us how much propellant mass flows through the engine per second, which is written as m dot. In formula form, the mass flow rate is given by an expression involving throat area, total pressure, total temperature, and gas properties. In words, the mass flow rate is equal to the throat area multiplied by the total pressure divided by the square root of the total temperature multiplied by the square root of the specific heat ratio divided by the gas constant and multiplied by the quantity 1 plus the specific heat ratio divided by 2, raised to a negative exponent that depends on the specific heat ratio. Physically, this means the combustion chamber and throat act like a metering device that controls how much mass can escape per second. Once the mass flow rate is known, the next question is how fast the gas is moving when it leaves the nozzle. To find that, we need the exit Mach number m sub e. The image gives an area, Mach number relation that connects the exit area a sub e to the throat area a star. In formula form, this equation relates the ratio of exit area to throat area to a function of the exit Mach number and the specific heat ratio. In words, the exit area divided by the throat area is equal to 1 divided by the exit Mach number, multiplied by a term involving 2 divided by the quantity gamma plus 1, multiplied by the quantity 1 plus the quantity gamma minus 1 divided by 2 times the exit Mach number squared, and the entire expression is raised to a power that depends on gamma. This equation comes from compressible flow theory and tells us that for a given gas, a larger exit area produces a higher exit Mach number. After determining the exit Mach number, we can calculate the exit temperature. The image shows the ratio of exit temperature to total temperature. In formula form, this ratio depends on the exit Mach number and the specific heat ratio. In words, the exit temperature divided by the total temperature is equal to 1, plus the quantity gamma minus 1 divided by 2 times the exit Mach number squared, and this entire quantity is raised to the power of minus 1. As the Mach number increases, the temperature decreases because internal energy is converted into kinetic energy. Next, the exit pressure is calculated using a similar relation. In formula form, the exit pressure divided by the total pressure depends on the same Mach number term, but raised to a different power. In words, the exit pressure divided by the total pressure is equal to 1 plus the quantity gamma minus 1 divided by 2 times the exit Mach number squared, raised to the power of minus gamma divided by the quantity gamma minus 1. This shows how rapidly pressure drops as the gas expands through the nozzle. Once we know the exit temperature, we can compute the exit velocity. The exit velocity equation relates velocity to Mach number and the local speed of sound. In words, the exit velocity is equal to the exit Mach number multiplied by the square root of the specific heat ratio times the gas constant times the exit temperature. This velocity represents how fast the exhaust gases are leaving the nozzle. Finally, we arrive at the most important equation on the page, which is the thrust equation shown in the red box at the bottom. The thrust F is the sum of two terms. In formula form, thrust equals the mass flow rate times the exit velocity plus the exit pressure minus the ambient pressure multiplied by the exit area. In words, thrust is produced first by the momentum of the exhaust leaving the engine and second by the pressure difference acting over the nozzle exit area. When a rocket operates in a vacuum, the ambient pressure P sub 0 is nearly zero, so the pressure thrust term becomes very large and positive. At sea level, ambient pressure reduces this contribution. This explains why the same rocket engine produces more thrust in space than it does on the launch pad. Putting everything together, this image shows a complete cause and effect chain. High pressure and temperature in the combustion chamber set the mass flow rate. The nozzle geometry determines the exit Mach number. The Mach number determines exit temperature, pressure, and velocity. The exit velocity and pressure difference then combine to produce thrust. This single page captures the entire physics of rocket propulsion in a compact and powerful way, making it an excellent foundation for understanding how real rocket engines are designed and analyzed. Specific impulse. Thrust is the force that moves a rocket through the air or through space. It is generated by the rocket engine through the reaction of accelerating a mass of gas. The gas is accelerated to the rear, and the rocket is accelerated in the opposite direction, according to Newton's third law of motion. To accelerate the gas, a propulsion system is required. For now, we can think of the propulsion system as a machine that accelerates a gas. Detailed descriptions of various propulsion systems will be covered later. From Newton's second law of motion, force can be defined as the change in momentum per unit time. Momentum is the product of an object's mass and velocity. When dealing with gases, the basic rocket thrust equation is thrust equals mass flow rate of the exhaust at the exit multiplied by the exhaust velocity at the exit minus the free stream mass flow rate multiplied by the free stream velocity plus the difference between the exit pressure and the surrounding pressure multiplied by the exit area. For liquid or solid rockets, all propellants, fuel and oxidizer are carried on board, so no free stream air is drawn in. This simplifies the thrust equation to thrust equals mass flow rate of the propellant leaving the rocket multiplied by the exhaust velocity at the exit, plus the difference between the exit pressure and the surrounding pressure multiplied by the exit area. Here, m dot represents the mass flow rate of the propellant leaving the rocket. Dividing the thrust equation by m dot gives thrust divided by mass flow rate equals exhaust velocity at the exit, plus the difference between the exit pressure and the surrounding pressure multiplied by the exit area divided by the mass flow rate. We define a new quantity called the equivalent velocity, V equivalent, as the right-hand side of the equation. Equivalent velocity equals exhaust velocity at the exit, plus the difference between the exit pressure and the surrounding pressure multiplied by the exit area, divided by the mass flow rate. The thrust equation can then be written more compactly as thrust equals mass flow rate multiplied by equivalent velocity. This form is convenient because it combines the contributions of momentum and pressure into a single effective velocity term. The total impulse, I, of a rocket is defined as the average thrust multiplied by the total burn time of the engine, delta T. Total impulse equals thrust multiplied by burn time. If the thrust varies with time, the total impulse can be expressed as an integral. Total impulse equals the integral of thrust with respect to time. Substituting the thrust equation in terms of equivalent velocity. Total impulse equals the integral of mass flow rate multiplied by equivalent velocity with respect to time. Assuming V equivalent remains constant over the burn time, the integral simplifies to total impulse equals total mass of the propellant consumed multiplied by equivalent velocity, where m is the total mass of the propellant consumed. The specific impulse, ISP, is defined as the total impulse per unit weight of propellant. The word specific means per unit weight. It can be written as specific impulse equals equivalent velocity divided by standard acceleration due to gravity, where g0 is the standard acceleration due to gravity, 9.8 meters per second square in metric units or 32.2 feet per second square in English units. Using the thrust form of V equivalent, the specific impulse can also be written as specific impulse equals thrust divided by the product of mass flow rate and standard gravity. Why specific impulse matters? Specific impulse is a crucial parameter because it tells us how efficiently a rocket engine uses its propellant. There are several reasons we care about it. 1. Quick determination of thrust. It allows engineers to calculate the thrust of a rocket quickly if the propellant weight flow rate is known. 2. Engine efficiency. Specific impulse indicates engine efficiency. Two engines may use the same amount of propellant, but the one with higher ISP produces more thrust. 3. Simplifies analysis. It makes thermodynamic and performance calculations easier. Its units remain consistent across English and metric systems. 4. Engine sizing. During preliminary design, ISP helps determine how much propellant mass flow is needed. Dividing the required thrust by the specific impulse gives the propellant flow rate, which in turn helps define the physical size of the engine and propellant tanks. In summary, specific impulse not only gives a quick way to estimate thrust, but also serves as a measure of engine efficiency, simplifies calculations, and guides engine design. A similar performance parameter used for turbine engines is called specific thrust, which characterizes their efficiency. Ideal rocket equation. The forces acting on a rocket change dramatically during a typical flight. During powered flight, propellants are constantly expelled through the nozzle. As a result, both the mass and weight of the rocket are constantly decreasing. Because of this changing mass, the standard form of Newton's second law cannot be directly used to determine the rocket's acceleration and velocity. To account for the changing mass, we derive the ideal rocket equation, neglecting aerodynamic lift and drag for now. These effects can be added later. Consider a rocket with instantaneous mass m moving at velocity u and ejecting mass at exhaust velocity. Let A be the nozzle area, P the exhaust pressure, and P0 the atmospheric pressure. During a small time interval dt, a small mass dm is expelled. The change in momentum of the rocket is change in momentum of the rocket equals mass of the rocket multiplied by the change in velocity. The change in momentum of the expelled mass is change in momentum of the exhaust equals negative exhaust velocity multiplied by expelled mass. Thus, the total change in momentum of the system, rocket plus exhaust, is change in momentum of the system equals mass of the rocket multiplied by the change in velocity minus exhaust velocity multiplied by expelled mass. Neglecting aerodynamic drag, the forces on the rocket are weight equals mass of the rocket multiplied by gravitational acceleration, acting at an angle alpha to the flight path. Pressure force equals nozzle area multiplied by the difference between exhaust pressure and atmospheric pressure, acting along the direction of motion. The total force on the system is total force equals nozzle area multiplied by exhaust pressure minus atmospheric pressure, minus mass of the rocket multiplied by gravitational acceleration multiplied by cosine of alpha. From Newton's second law, the change in momentum equals the impulse, force multiplied by time. Mass of the rocket multiplied by change in velocity minus exhaust velocity multiplied by expelled mass equals nozzle area multiplied by pressure difference minus weight along flight direction multiplied by the time interval. If we neglect gravity and simplify, mass of the rocket multiplied by change in velocity equals nozzle area multiplied by pressure difference multiplied by time, plus exhaust velocity multiplied by expelled mass. Since the expelled mass dm equals the mass flow rate m dot times dt. Expelled mass equals mass flow rate multiplied by time. The equation becomes mass of the rocket multiplied by change in velocity equals nozzle area multiplied by pressure difference plus mass flow rate multiplied by exhaust velocity multiplied by time. We define the equivalent exit velocity V equivalent as equivalent velocity equals exhaust velocity plus nozzle area multiplied by pressure difference divided by mass flow rate. Substituting into the momentum equation. Mass of the rocket multiplied by change in velocity equals equivalent velocity multiplied by mass flow rate multiplied by time. Because the rocket is losing mass, the change in mass is negative. Mass flow rate multiplied by time equals negative change in rocket mass. Substituting gives mass of the rocket multiplied by change in velocity equals negative equivalent velocity multiplied by change in rocket mass. Dividing both sides by m. Change in velocity equals negative equivalent velocity multiplied by change in mass divided by mass of the rocket. Integrating from the initial mass to the final mass. Change in velocity equals equivalent velocity multiplied by natural logarithm of initial mass divided by final mass. Rocket mass definitions. The instantaneous mass of the rocket is the sum of its empty mass and the remaining propellant mass. Rocket mass at time t equals empty mass plus remaining propellant mass at time t. At launch. Initial mass equals final mass of fuel plus empty mass. At the end of the burn, final mass equals empty mass. Substituting these values into the velocity equation. Change in velocity equals equivalent velocity multiplied by natural logarithm of initial mass divided by empty mass. This is known as the ideal rocket equation. Propellant mass ratio. Defining the propellant mass ratio MR as propellant mass ratio equals initial mass divided by empty mass. The ideal rocket equation can also be written as change in velocity equals equivalent velocity multiplied by natural logarithm of the propellant mass ratio. Since equivalent velocity is related to the specific impulse. Equivalent velocity equals specific impulse multiplied by standard gravitational acceleration. Thus, the ideal rocket equation in terms of specific impulse is change in velocity equals specific impulse multiplied by standard gravity multiplied by natural logarithm of the propellant mass ratio. If the desired change in velocity is known, we can invert this equation to calculate the required propellant mass ratio. Propellant mass ratio equals the base of the natural logarithm raised to the power of change in velocity divided by the product of specific impulse and standard gravity. Example, orbital launch. Consider a liquid hydrogen-liquid oxygen rocket, such as the Space Shuttle main engine. Suppose specific impulse approximately equals to 350 seconds. Change in velocity needed to reach a 200-mile orbit approximately equals to 17,000 miles per hour or 25,000 feet per second. Standard gravity equals to 32.2 feet per second squared. Using the ideal rocket equation. Propellant mass ratio equals e raised to the power of change in velocity divided by the product of specific impulse and standard gravity, approximately equal to 10. This means 90% of the rocket's launch weight is propellant, while the remaining 10% includes structure, engines, and payload. The payload itself may only be about 1% of the total launch mass. This demonstrates why rockets are currently very inefficient and expensive. If gravity is included during the burn time Tb, the ideal rocket equation becomes: change in velocity equals equivalent velocity multiplied by natural logarithm of propellant mass ratio minus standard gravity multiplied by burn time. This equation provides a more realistic estimate of velocity change during powered flight. Okay guys, now let's have a little quiz. The quiz consists of 10 questions. I'll give you 10 seconds for each one, and then I'll show you the correct answer. Let's start with the first question. Question 1. What physical quantity does the term mass flow rate describe in rocket propulsion? The correct answer is the amount of exhaust mass expelled per unit time. Question 2. What happens to the acceleration of a rocket as its mass decreases during powered flight, assuming thrust remains constant? The correct answer is the acceleration increases. Question 3. Why do rockets operate effectively in the vacuum of space? The correct answer is they carry both fuel and oxidizer on board. Question 4. In the generalized rocket thrust equation, which term accounts for pressure differences at the nozzle exit? The correct answer is the difference between the exit pressure and the surrounding pressure multiplied by the exit area. Question 5. Which parameter directly determines the mass flow rate through a rocket nozzle when the flow is choked? The correct answer is throat area. Question 6. In the ideal rocket equation, what does the mass ratio mR represent? The correct answer is the ratio of empty mass to propellant mass. Question 7. What is the primary role of the nozzle in a rocket engine? The correct answer is to accelerate exhaust gases and increase thrust. Question 8. In the ideal rocket equation, what quantity does delta U represent? The correct answer, the change in velocity of the rocket. Question 9. Why is the exhaust flow said to be choked at the nozzle throat? The correct answer is the Mach number equals 1.0 at the throat. Question 10. According to the rocket equation, including gravity losses, what additional factor reduces the achievable change in velocity? The correct answer is burn time multiplied by gravitational acceleration. Unlock the world of aerospace engineering with my other expertly designed courses. In Aerospace Engineering, Basics of Aviation Engines, you'll explore the different types of aerospace engines and how they perform, giving you a strong foundation in the propulsion systems that power modern aircraft. Then, take your knowledge to new heights with Aerospace Engineering, Aerodynamics and Structures, where you'll dive into the design and performance of aerospace structures and their aerodynamic behavior. Finally, expand your expertise with Aerospace Engineering, Avionics and Aerospace Systems, where you'll learn about the critical electronic systems that control and monitor modern aircraft, bridging the gap between engines, structures, and flight systems. Whether you're a student, aspiring engineer, or aviation enthusiast, these courses will equip you with essential knowledge to understand and contribute to the future of aviation. Join hundreds of learners and start building your aerospace journey today. Thank you guys for watching this video. If you have any questions about this lesson, feel free to ask me in the comment section. I will answer as soon as possible. We can continue to the next lesson and learn about understanding rocket weight, calculations, and center of gravity. See you in the next video. Bye.